Welcome to the electromagnetic theory and interference course. In this session, let us discuss about the Maxwell equation for static case, and we will see how the Faraday law is useful for getting the Maxwell equation for a time varying field. So we already saw all the four equations in the previous sessions. Let us summarize now the Maxwell equation for static, electric and magnetic field. Let us see first in differential form or point form. The Gauss's law for the electrostatic field states that divergence of electric flux density is equal to rho v. This we know. And divergence of magnetic flux density is equal to 0 for the magnetostatic field, which represents the non-existence of magnetic monopole. This we saw just in the previous session. So two divergence we saw. Now we are going to see two curl of the field intensity. One is electric field intensity, that is going to be 0. Okay, curl of the electric field intensity is 0, which shows the conservative nature of electrostatic field. Whereas curl of the magnetic field intensity is equal to J, that is current density, by application of the Ampere's circuit law. So let us see how to write these four equations in integral form. So here if you observe, the divergence have to be represented by the closed surface integral of the vector, and it should relate to the volume integral of the open volume integral of the other side of the equation. Okay, so surface integral of d dot ds is equal to what? Volume integral of rho v dv. Whereas here if I take closed surface integral, it is going to be 0. Whereas for the curl, what we have to do, we have to take closed line integral of the same vector, and on the opposite, on the left right hand side, I have to take open surface integral. And here it is 0, so you can't see here, but in this Ampere's law, you can see the closed line integral of h dot dl is equal to open surface integral of surface current density J into ds. Okay. So for a particular problem, how we can choose whether we need a differential form or integral form, it depends on the nature of the problem. And a vector field, we all know that it is completely specified by its curl and divergence. So only we are arriving in the Maxwell equation also the same. And when my field is electric or magnetic, only if it is satisfy the corresponding Maxwell equation. If it is going to satisfy only, it is going to be an electric or magnetic field. And we can observe, actually we will see in the after discussion in the last session, that divergence equation C, the highlighted red color divergence equation, we're going to be same for the time varying electromagnetic field also, that we are going to see in the upcoming session. But curl equations have to be modified. These things are going to be modified in this session. Using the Faraday law, we will see how the curl of the electric field vector is going to be modified from its conservative nature. For the time varying case, what change is going to be, that we are going to observe. Let us see about Faraday's law. So before coming to Faraday's law, we need to know that Oersted experimentally discovered that studies current is going to produce a magnetic field, and based on that only Biot-Savart and Ampere's law came up, and we should logically find out whether the magnetism is going to produce electricity. This is the thing we are going to observe here. So after 11 years of Oersted discovery only, Faraday and Henry, okay, both of them discovered that time varying magnetic field that is going to produce an electric current. Okay. So Faraday's experiments, what they come up with, that static magnetic field produces no current flow. We already know. But in a closed circuit, a time varying magnetic field produces an induced voltage called electromagnetic force or EMF, that is going to cause the flow of current. Okay. Static magnetic field, no current. But in a closed circuits, time varying magnetic field produces induced voltage that will result in a flow of current. So now let us see how the Faraday's law can be expressed mathematically. So as you can see, the induced EMF in any closed circuit is equal to time rate of change of magnetic flux linkage in the circuit. The flux linkage is lambda here, and we will see how this negative sign comes. Okay, it is this flux linkage is going to be n into psi. So number of turns in the circuit in the flux through each turn. So I can rewrite this VMF as minus n into d psi by dt. So the negative signs, what does it indicate? The induced voltage is going to act in a way such that it is opposing the flux that is producing it. The opposing nature only is represented by negative. This is called Lenz's law. This behavior is called Lenz's law. State that direction of current flow in a circuit is such that the induced magnetic field produced by the induced current opposes the change in original magnetic field. Okay, this is my Lenz's law. We already know that electric charges experience a force called electric field, and the electric fields are caused by the electric charges, and the flux lines behind and end on the same charge only. It started the charge and it ended the same charge. Whereas electric field of other things like EMF, right, they are not directly caused by electric charges. Okay, the sources of EMF may be the electric generators, batteries, thermocouples, photovoltaic cells. So they are going to convert non-electrical energy to electrical energy. So we are going to see how the Faraday law link the electric and magnetic field. So this is our aim, right? For a circuit with a single turn, I can rewrite this VEMF as, instead of n, I can replace by 1, that is minus d psi by dt. We already know the we are going to apply the already found expressions for EMF, that is volt potential is going to be the EMF, right? That I can write as a closed line integral of E dot dl, that is from the first unit, electrostatic field. And flux I can replace by surface integral of magnetic flux density, right? So I can rewrite minus d by dt of integral of b dot ds. So both a side of equations I replace. Now I am going to apply the Stokes theorem for the middle term. So we already know closed line integral of vector is equal to open surface integral of curl of the same vector. So I can rewrite this as surface integral of del cross E dot ds is equal to the same minus d is going to be within the integral dou b by dou t dot ds, right? And if I compare both the surface integral, del cross E is equal to minus dou b by dou t, and we can observe that this is the Maxwell's equation, third equation, right, for the time varying case. And we can observe that this is not equal to 0. It shows that time varying electric field is not conservative in nature. And we should know how can I bring about a variation of flux by having a stationary loop in a time varying field, or a time varying loop in a stationary magnetic field, or a time varying loop in time varying field. I can bring about the change in flux or the variation of flux so that EMF is induced. So I hope you understood how the Faraday's law is used to find the Maxwell's equation for the time varying field. Right? Thank you, everyone.